In this last video for Lab 5, I'm going to walk very briefly through example 3. It is also a Latin square. In this case, it's a 3 by 3 Latin square. In this experiment, what we're looking at are 3 gasoline additives. So we have 3 different treatments, A, B, and C, that we're adding to gasoline. And we're looking at their effect on combustion efficiency. And the way we do this is by measuring the amount of carbon monoxide that's coming out of the exhaust pipe. So if you have better combustion efficiency, you have lower levels of carbon monoxide. Great. So in the end, the objective of the study is to evaluate which one of these treatments helps increase combustion efficiency the most. That being said, the experimenters recognize that when running a study like this, there are many things that can contribute to differential combustion efficiency that would have nothing at all to do with the treatments themselves, and that those things are potentially adding noise to the study, noise into the data set, and would make seeing differences among treatments that much harder to detect. Some of those things, one of those things that could cause variation are drivers themselves. Some people are lead foots, other people aren't, and the way in which you drive can greatly have great effects and greatly influence combustion efficiency. So this human effect, they want to block by driver. In other words, they want to make sure that differences in the way people drive do not color their conclusions about the effects of gasoline additives. So driver is a good blocking variable in this particular case. Something else that can cause differences in combustion efficiency are simply different tractors. Tractors are not all tuned up to run in tip-top shape. There's a spectrum there. Some are inherently more efficient than others, better seals, better gaskets. And so you don't want differences among your tractors also coloring your conclusions about treatments. And so in this particular case, tractor is also a good blocking variable. This is going to be a replicated Latin square. So it's a Latin square because we have 2 different blocking variables, drivers and tractors. I'm going to call these rows and columns. And we have our 3 treatments. So there's the 3 by 3 constraint, 3 rows, 3 columns, 3 treatments that we would expect in a Latin square. And in this particular case, it's replicated because the experiment was carried out twice on 2 different days. Let's go ahead and look at the data set. I've opened up in the script. This is example 3, lab 5. Here's the script, and I've brought in the data set associated with that, also called ls.dat. And you'll notice in this data set, we have not only the treatment, the driver, and the tractor, so the 2 blocking variables in the treatment and the response. We also have this day column because the experiment was run twice. This day column is essentially square. If tractor is row and driver is column, day is square. We have square 1 and square 2, and each of these squares has 9 values because the squares are 3 by 3s. So we end up getting, in effect, a 4th classification variable that we need to deal with in the model. To read in the data set, look at it, it's unfortunately interpreting square, row, and column as integers instead of factors, so we need to reassign them as factors. And here we're looking good. Row, column, and treatment are all factors with 3 levels, and we run it over 2 days, so it's a factor with 2 levels. Now, when you run the model, you have several options here. And I would say you have several options not because you would run it many different times, but because you would run it once based on what the real situation, what the real experimental situation was. One of the situations would be, let's start easy. One of the situations would be a replicated Latin square in which the drivers and the tractors are the same on both days. So this is replicated Latin square sharing rows and sharing drivers. In other words, in the entire study, I only have 3 drivers and I only have 3 tractors. In this case, the model is pretty simple. It's your response variable, the level of carbon monoxide, is explained by the day, And you'll see here that day is essentially acting as a third blocking variable. It's something that we can assign variation to. You can imagine that combustion efficiency may have a lot to do with ambient environmental effects, temperature, humidity, pressure, that kind of thing. So you may have differences day to day that, again, you don't want to confound your conclusions about the additives. So day enters the model and essentially acts as another blocking variable. Tractor is there, driver is there, and treatment is there. This looks just like our unreplicated Latin square model from example 2, and the only thing we've added on is this third blocking variable. And you can run that, and what you'll see is that R understands there to be 3 tractors because there's 2 degrees of freedom. There are 3 drivers in the experiment, 2 degrees of freedom, and there are 3 treatments in the experiment, 2 degrees of freedom. Perfect. So it understands everything correctly, runs the analysis, and then you could go and start testing assumptions in the way we did before. Another possible way of replicating a Latin square is where drivers and tractors are not shared between the 2 days. In other words, the 3 drivers on day 1 are not the same 3 drivers on day 2, and the same with the tractors. In that particular case, you need to let R know that, and this is the syntax for that. Day appears as it did before, treatment appears as it did before, but now tractor appears with day in front of it followed by a /. In other words, it's telling you that tractor is nested within day, or the level of tractor only makes sense if you specify which day you're talking about. Tractor 1 on day 1 is not the same as tractor 1 on day 2, and the same with driver. If you run this particular model, I'll show you what I mean. You'll notice that the degrees of freedom change a little bit. I still have 3 treatments, 2 degrees of freedom. I still have 2 days, 1 degree of freedom. But you'll notice that my tractor degrees of freedom increased from 2 in the first study to 4 in this study. We have 4 degrees of freedom because we have, in fact, 6 different tractors in the study. 3 on each day, 2 degrees of freedom for each day. And the same with driver. You won't be surprised to learn that this adjustment in degrees of freedom throws everything off. So you get different error values, you get different F values, different P values. And if this were the case, where you really were not sharing tractors or drivers, this would be the correct analysis to run. And then, of course, you can have variations on the theme. You could have it such that the drivers, the 3 drivers are the same on both days, but the tractors aren't. In that particular case, tractor would be nested within day, but driver would not be. If you run that model, you would get degrees of freedom that reflect that. I have 2 degrees of freedom for driver in the entire study, but I have 4 degrees of freedom for tractor in the entire study. And that's because drivers are shared, tractors are not shared. Or you can flip it around the other way, where tractors are shared, but drivers are nested within day. I'll say again, you would use, if you had a replicated Latin square, this is a good script to go back to grab some code as a template, but you would only grab one of these examples as your template. You would not run all 4 or 5 analyses. You would run the analysis that is appropriate for the particular study that you're trying to analyze. And make sure there's no other things to discuss there. I would say, as with all of these, please look in detail at the lab handout. I've highlighted some things in the ANOVA tables to draw your attention to stuff. And also at the end of the lab, like I had in the lecture notes, I have this same sort of explanation about one way to think about the Tukey 1 degree of freedom test for non-additivity. So look at all that, and I think that's it for Lab 5.